To Einstein's mechanics. Today we are tackling the third episode for the problem solving in fluid mechanics. So we have problem 1. Two plates are separated by a 1/8 inch space. The lower plate is stationary. The upper plate moves at a velocity of 25 feet per second. And oil, that's the oil chosen, was psi 10W30 at 150 degrees Fahrenheit, which fills the space between the plates, has the same velocity as the plate at the surface of the contact. The variation in velocity of the oil is linear. What is the shear stress in the oil? So we have the information given and we are to determine the shear stress in the oil. So first we have to identify the oil being used. So the oil is this type of oil, that's psi 10W30 at 150 degrees Fahrenheit. So this is the oil used, which filled the space between the plates. Are we okay? So this is the oil. And we are given the plates are separated by 1/8 inch. So the separation between the plates, which is the distance between the plates, change in y distance. Remember the formula for shear, we are using change in y for the space between the plates, and that is 1/8 inch, which is also the same as 0.125 inches. Okay, and from the question, the lower plate is stationary. So an assumption is that the lower plate is stationary, not moving. You can state the assumption. The lower plate is what? Stationary, and we are to determine the shear stress. So what is the formula for the shear stress? We know that shear stress in relation to viscosity and shear strain is given as the viscosity du dy, which is the change in what, or the shear strain. Are we okay? Are we given the viscosity of the oil? Because the question says we are to find the shear stress in the oil. So what is the viscosity of the oil? This type of oil, what is its viscosity? And the viscosity of the oil can be obtained from tables. It is a constant value, psi 10W30. Its viscosity is a constant value at 150 Fahrenheit. And from tables, you can read its viscosity to be 5.2 10 to the power -4 IBF dot second per feet square. Are you okay? So this is the viscosity of the oil in use from tables. You can be given in the question, or when you have your tables, you can refer and find the viscosity of the oil. Very simple. So now we have the viscosity. How do we get the rate of strain? And from the question, we saw that the upper plate moves at a velocity of 25 feet per second. So do we have the velocity? Yes, which is represented by u, and that is 25 feet per second. Let's pay attention here. Feet per second. So how do we get the strain? Strain du dy. Can we say du dy calculus is the same as change in u, change in y? Yes. And we have our u and we have also the y. So we can say the rate of strain, which is du dy, is the same as the u, which is 25 feet per second on the change in y, which is the distance between the plates. Check the unit. You can see that the unit for the viscosity is per feet square. The unit for the velocity is feet per second, but therefore the distance between the plate is in inches. So we have to convert the inches to what? Feet. And to convert inch to feet, you have to divide by 12. So this, which is change in y, will be our 0.125 divided by 12 to convert from inch to feet. Very good. So that will be feet now. And this du dy is going to give us du dy, that's the rate of strain, will be 2400. Look at the unit per second. Are you okay? So therefore, we can say that the shear of the oil with a viscosity of 5.2 times 10 raised to the power negative 4 multiplying the rate of strain, which is 2400, is going to be 1.25 pound force per what? Feet square. Are we okay? So this is the shear stress in the oil. Are we good? We knew that this is the space in inches. We convert it to what? Feet. You can go through it again and it will help. This statement, the variation in viscosity of the oil is linear, makes us understand that we can use this formula to calculate for the shear. Are we okay? Under the condition that the velocity is linear. Let's look at example 2. The velocity distribution for the flow of crude oil. So pay attention, this is crude oil at 100 Fahrenheit. This is the viscosity. You see, for here, we were given the viscosity. If you are not given, you refer to tables and you obtain it. It's 8 to the power negative 5 pound force per second per feet square between two walls is shown. And we have the velocity given, u. Remember, this is mu, and it is different from that. U, which is the velocity, is given as 10, this equation, feet second, where y is measured in feet and the space between the walls is 0.1 feet. Plot the velocity distribution and determine the shear stresses or the shear stress at the walls. Are we good? So I'm interested in finding the shear stress at the walls. So let's see what we can do. So first, let's write down our parameters. We were given a temperature of 100 Fahrenheit. We have it, and from crude oil at 100 Fahrenheit, its viscosity mu is giving us 8 to the power negative 5 IBF second per feet square. So we have it between the walls, and its velocity is given. So the u is different from the mu. Check the symbol. So the velocity u is giving us 100y 0.1. This is an equation, feet per second. So we have it, where y is the distance measured in feet. Are we okay? And the distance between the walls is also given as what? 0.1 feet. We know that y is the distance or the space, so y is given as 0.1 feet, and we have to determine the shear stress. Are we good? So here we know that our shear is going to be mu du on dy, but we have our du dy. We can obtain that from the equation. Now, The velocity is given in an equation form which involves what? Y. So I can differentiate the u with respect to y and get my rate of strain. So du dy is now going to be equal to, so first, if you differentiate this with respect to y, you are going to get 10 minus 200 y squared. This is the same as the rate of strain. Yes, calculus. Differentiate this and you are going to get 10 minus 200 y squared. And at the walls, this is going to tell us that there is a movement between two walls. The first one, which is A, and the second one, which is what? B. The difference here, or the distance, is 0.1, and we are to determine the shear at the walls, which means at A and at B. Are we good? Meaning at the walls, this started from 0 and got to 0.1. So what is the shear at A when y was 0 and at B when it was 0.1? These are the shear stresses we are to determine. So first I can say at the A point, at A, where y is equal to 0, there is no distance between the walls. What is the shear stress at that wall? And that is going to give me my shear is equal to, from the formula, the viscosity, 8 to the power negative 5, multiplying du dy. But here, this is the relation for du dy, and the y is what? 0. So that is going to be 10 minus 200 0 squared this way. And when you punch this, you are going to get the shear at 0 is 8 to the power negative 4 IBF per feet square. So this is the shear at the point A equal to 0, or when y is 0, that is 8 to the power negative 4 IBF per feet square. So let's see the stress, the shear stress at a distance 0.1, the upper wall. This represents the shear at the stationary part, the lower wall. So at y equals 0.1, what is the shear stress over there? So can I say shear at 0.1 is equal to the same formula, the same oil, so the same viscosity, which is 8 to the power negative 5 multiplying the strain. Here it is 10 minus 200, and this y is now 0.1 squared this way. And when you punch that, this is going to give you the shear at 0.1 to be a negative value, a negative 8 IBF per feet square. So since it's shear stress, we can say shear at 0.1 is also 8 negative 4 IBF per feet square. This negative is just giving us an indication that it is a negative what? Shear, meaning to the opposite direction. Are you okay? So they are both going to experience the same shear at the lower plate and at the upper plate with a shear of 8 times 10 to the power negative 4. So thank you for watching this episode. Check out for the next set of questions.